Okay, so we're in section 18.6, clampers, DC restorers. A circuit is designed to shift a waveform either above or below some reference voltage. So let's say that I've got this hunk of wire and it's 500 feet long, and I got the signal going up and down on it, and it goes 0 and 5 volts. Am I going to make it to the other end of that wire?
Yes.
And the answer is no, I'm not. The resistance of the wire is going to take away my signal. It's not going to work. But if I throw a DC component on that, and my signal goes 15 volts to 10 volts, so that's my signal going there. And so I got this DC component down here that's 10 volts big. Then that 10 volts big DC component is going to push me down the wire, and I'm going to end up seeing my signal at the output. And then I can just get rid of whatever DC is associated with it, and I can get the signal all the way down the 500-foot wire. Now, do I want you guys taking 500 feet of my wire and spreading it around the lab to see if... No, I don't. No, I don't. No. We're not going to do that. But that's the purpose of the clamper, is to either get rid of some DC or to add some DC to it. So here we have a signal that's 20 volts peak to peak. I add a positive clamper, and now I got it up a little bit. I add a negative clamper, I go down a little bit. So that's the whole purpose. Now, why would I want to get rid of the signal? I'm not so sure why I'd want to do that. But, the same thing happened to the first transatlantic cable that was put in. It was $5 million worth of cable just after the Civil War, and it only lasted for about a day. The guys added too much DC to it and burned up the cable. And technician problem, typical, right? They blame us for everything. So what I do is I end up throwing in a capacitor and a diode together. So now on the positive half cycle, I end up passing to ground. On the negative half cycle, I end up going through my load. And there's some time constant associated with the resistance of the diode times C1, the resistance of the capacitor times C2. So we end up having a signal that's like that. We send it through the clamper, and now we end up with a negative signal as my capacitor charges and discharges, either discharges through the diode or discharges through the load as I'm going positive and negative. So I'm going to use a diode and a capacitor to do that. If I want a positive, thank you very much, marker. If I want a positive clamper, I put the diode in the other way. So now that when I'm on the positive side, I can't make it through the diode. When I'm on the negative side, I do go through the diode. So that's how I get a positive or a negative clamper. And then depending on the size of my capacitor, will decide on how far I go. Biasing the clampers. So now I want to go, I only get a 0.7 volt out of that diode. So now I can bias the clamper by throwing in some more resistance for some more voltage. So I throw voltage on the other side of the diode, and now I can make it go higher, I can make it go lower. I can also use a Zener diode for the same purpose. So if this is a 7-volt Zener diode, then that would have the same effect as if I had a 7-volt DC power supply, because the Zener diode is going to maintain 7 volts. That would be the same as a negative 7-volt battery sitting there type thing. Positive battery, negative battery. So depending on, and then I can buy a Zener diode pretty cheaply. They're 14 cents a piece, and so I don't necessarily have to have a battery that's discharging, a power supply that's discharging using power. I just use the fact that Zener diode is going to do that for me. Voltage multiplication. I've got 120 volts and I want 240, or I want 360, or I want some other voltage. So I have circuits that can multiply voltage. So here I've got a circuit, and because my currents are going the wrong way in the picture, we'll go and put it in here and make the currents go the other way. So on the negative half cycle, my current is going that way, charging up the battery, plus charge on this, the capacitor plus charge on this side, then a negative charge on that side. Because it's positive half cycle, I can't make it through that diode, but I can make it through this diode, and I'm also charging up the other battery. So I have current coming this way, charging up that battery. On the positive half cycle, I have current flowing that way, and that way, and that way. Now I have current flowing, getting me charging up the other capacitor. So on the negative half cycle, I charge up that capacitor. On the positive half cycle, I charge up the other capacitor. Now this guy's charged up to as high as my voltage is. That guy's now charged up to as high as my voltage is, and I end up having more charge, and I double my voltage. Anybody convinced of that? Probably not. We'll probably have to put it in multi-sim to see it. But I end up, I have some secondary peak, and my voltage doubler is now going to make the get my voltage twice as high. I used to be there, now I'm down here. That guy's going up, this guy's being turned the other way, and he's going up. I have a ripple that's sitting on top. So I need a better way to kill my fellow man, and 480 volts won't do it. I do a voltage doubler and get him at 800 and some. No? Yeah, I could. Yes. Question.
Is that what is a voltage doubler, or not a multiplier? It's kind of thing you use in an electric fence to ward off like deer or whatever you patches for people?
Definitely not. No. You're using an inductor and a capacitor together at resonance to have a really high voltage, because you don't at the lower voltages you're going to end up killing the thing. At the higher voltages where you have less amps being passed on, now the shock is there, but you're living through it. So
yeah,
at 480 volts and I double it to 800 and something, I'm going to kill the deer.
I was wondering because my dad and I were setting one up a while ago. He was reading 6K, 7K volts, which I didn't touched it, and I got knocked on his ass.
Yeah, exactly.
I was dead for a second.
Yeah, yeah, yeah. But 7,000 volts is a nice amount of voltage, yes. But there's not much amperage behind it because of the circuit. Whereas this circuit's going to deliver amps as well, and that would not be good for.
Don't touch that one.
Yeah,
I was confused about that.
Yeah, but it didn't, So when we executed people, we didn't execute them with any voltages higher than 480. We just, apply the electricity until the blood inside their heart boiled and burst the thing open, and took a couple minutes, But that was the whole purpose, right? Yeah. Well, the whole purpose wasn't to be nice about it. Yeah. Okay, so here's a full wave doubler. So I'm coming one way, I'm coming the other way. I have 3 capacitors now that are going to double, give me twice as much peak voltage to the load as what the AC signal is. And I can go on and I can have a voltage tripler. So I throw in another capacitor, I can throw in another diode, and now I'm going to triple the voltage at the load. Now whenever I triple the voltage, I've also cut the current in a third, right? Because I'm going to have the same power coming from my power supply. It's not like I gained any power. So voltage times current has to be the same. if my voltage supply is only putting out 1 watt, then I can only have 1 watt on the other side. So if I triple the voltage, I have to have 1/3 the current. Okay, so we could add voltage triplers and voltage quadruplers. Throw in another capacitor, throw in another diode, and now I'm quadrupling the voltage on the output of the circuit. Interesting circuits. You'd be hard-pressed to find one in applications. They can be made, but be hard-pressed to do. Okay, so it looks like we're done with our transparencies, and we're ready to work the homework problems. Anybody know where we stopped?
25 was the last one we did.
Okay, so 25. So we have only have 4 to do. 4 to do.
We didn't do it though.
No, we didn't do it.
We didn't do, I got 35.
I didn't do 35? Okay, the potentiometer in the guy below is set so the anode of diode D1 is at -2 volts. Assuming that the voltage source is 14 volts peak to peak, determine the peak load voltage and the current and draw the waveform. Okay, so we'll draw the waveform. Well, we'll draw the circuit first, and then we'll draw the waveform second. So I've got a 150 ohm resistor that's current limiting. That's going to keep me from blowing up my, what is this thing called anyway? My diode, that's what it is. And then I got some, I got -2 volts sitting right there. And I got something sitting there. And I got something out here, R load 1.5K. And from a technical point of view, I should be slightly more professional in being able to write on the board, right? Slightly. All right, well, that's as slight as I'm going to be. All right, so now the issue is my input voltage is going to do that. Vn. And I'm going to go 14 peak to peak. So I'm going to go +7, and I'm going to go to -7. Okay. Now, on the positive half cycle, this is reverse biased, so I'm going to see the positive half cycle. So on the positive half cycle, everything's fine in the world, and my voltage out is going to be what it is. Now, when I start getting negative, what I want to do is I want to forward bias this diode. So that means I'm at -2, so at -2.7 volts, I'm going to be forward biased on the diode. So I'm going to come down, and when I get to -2.7 volts, I'm going to pass through the diode, and now I'm passing everything to ground. And then I'm going to come back up, I'm going to come down, I'm going to cut off again, and I'm going to do the same thing over again. So I'm going to cut off at 2.7 volts. Okay, so that's what's happening. Now the other issue is, what is the determine the peak load voltage. Is that all they want? Peak load voltage? All right. Peak load voltage. I'll spell it differently. Load peak. 7 volts. Assume blah blah blah, determine the peak load voltages for the circuit and draw the waveform. Okay, we're done. Should we build in a multi-sim and see if it works? Or do you believe me? You believe me? Okay. And 48. Draw the waveform for the circuit shown below and determine its peak voltage values. Okay. So I've got something that looks like that. I got a capacitor, 3.3 microfarads. I got a diode. I've got a Zener diode. I got 6 volts on that Zener. That's a 6 volt Zener diode. And I've got a resistor, RL. And I got 2K out here. And I'm going to look at my time constant for a moment. So my time constant is 3.3 microfarads times 2K. Okay, so that's 6.6. Okay, so that'd be 6.6 milliseconds. It doesn't say what I have 18 volts peak to peak here, but it doesn't say that I have 60 hertz. Can we assume 60 hertz? Maybe we can't, but I think we will anyway. So 60 hertz means 16.6 repeating milliseconds for the period of the waveform. This guy here is 5 times this guy, which is fully charged, is going to be pretty close to that. So I don't think we're not going to be able to discharge the capacitor all the way, is what I'm telling you. So the capacitor is going to be able to be charged. All right. So if I have 18 volts peak to peak on this guy, then this guy is going to charge up to 9 volts. When I go that way, I'm going to be charging. When I come this way, I'm not going to be discharging very much. So this guy's going to be charging up to 9 volts. All right, so I've got a positive 9 volts charging up there. Here I've got a Zener diode. On the positive half cycle, it's like I'm holding this up to 6. When I get above that 6, this guy is going to be discharging. He's going to be discharging pretty fast. So that means the best I can do on this guy is going to be the 6.7 volts that's seen by that diode. I got a 0.7 there, and I got a 6 there. So the maximum I'm going to have is 9 volts when I'm charging negatively and I can't get through there. When I'm charging on the positive half cycle, I'm going through here and I'm only charging at 6.7. So my waveform is going to go 6.7 to 9 as seen by that capacitor. So now we're going to draw, what are we supposed to do? Peak voltages. Okay, so we're going to draw okay, so I'm going to go to 9. We'll go to minus 9, and that's going to be my voltage in. And then my voltage out on the negative half cycle negative half cycle, I get to see it all. And on the positive half cycle, I get it cut off at 6.7. Is that what I said?
Yeah.
Okay. But my capacitor is going to raise the signal. Is the capacitor raising the signal? Yeah. So I end up, boom, back. All right. So I'm looking at a place where I'm at 9 volts. And because the capacitor is there, I'm going to go a positive half cycle. I'm doing that. So on the positive half cycle, I'm going to be going up until I'm cut off at 6.7 volts. And then I'm going to start coming down again, and I'm going to see the whole negative half cycle. And then I'm going to come back up, and I'm going to be cut off there. Right, so that's what I think I'm doing. So I'm going to come down to 0 volts. I'm going to 6.7 plus 9 is how much? 15.7. I'm going to come up to 15.7. 15.7 volts. Okay, this thing's not on touch. I don't know why it's doing that. Okay, I think that's what's happening there. 56. 56. The circuit shown below, peak voltage is 20 volts. Determine the voltage across capacitor 1, the voltage across capacitor 2, the voltage across capacitor 3, and the voltage across capacitor 4. Isn't that lovely? 56. Okay, so I've got something in 20 volts peak. Okay, 20 volts peak. And I have that guy, and I got this guy, and I got that guy, and I got that guy, and I got another one here, and he comes over to there, come across to there. Okay, capacitor 1, capacitor 2, capacitor 3, capacitor 4. All right, so now I'm looking at the positive half cycle, and I'm coming this way with charge. I'm charging up this capacitor. I can't go that way, and I've got a positive charge there and a negative charge there, and the negative charge can't go through him because that'd be reverse bias, and so this guy would charge to 20 volts. Okay, now he's at 20 volts. I'm on the negative half cycle. Okay, the negative half cycle, my current is flowing that way, charging him. So this guy's going to be at 20 volts. This guy's going to be at 20 volts. Looks like he's going to be at 20 volts, and he's going to be at 40 volts, I think. Well, On the negative half cycle, I'm coming this way. I'm charging him to 20. But when I come this way, I'm already 20 on here. What I do wrong? I'm missing a diode? Now you tell me. Was
We'll
such
tell
a
everybody if you
such a
want.
brilliant explanation too. Okay, positive half cycle, I'm doing that. And I'm coming, and this way I'm negative, so I'm coming back. Okay. Negative half cycle, I'm positive this way, positive that way, I'm positive that way, I'm charging, okay, positive, negative half cycle, I'm coming that way, coming that way, coming that way, across there. I think I have it. I think that's what it's supposed to be, a voltage doubler at 40, right?
4 diodes.
I only see 3 diodes.
Yeah.
So now we'll go back to our doubling and tripling circuits, and we see that this is basically the guy in on page 605. And 605 says I get 3 times. Okay. 3 times the voltage, but I messed up. Yeah, 3 times the voltage. That's supposed to go to 40. All right. So on the positive half cycles, that guy is okay. Back to the positive half cycle. Positive half cycle, he's charging to 20, he's charging to 20. Negative half cycle, he's charging another 20 to give us 40, he's charging 20 to give us 20. The 20 and 40 gives us 60 on the output. Okay, excellent. 67. Repeat problem 66. All right. Well, we're not going to repeat problem 66. We're going to do problem number 67. Number 67. So I've got this waveform that goes plus and minus 20 volts. All right, so that's what I got. I got some resistor. 10 ohm, that's not much of a resistor. I have 2 Zener diodes back to back. One's a 10 volt guy and the other one's a 10 volt guy. Okay, so I got 2 10 volt guys and I've got 1 resistor, R1, 1K. And what I'm supposed to do, use your knowledge of dial operator, determine the shape of the curve. All right. So I've got an input guy doing that. That's fine. Vn. 20 volts minus 20 volts. All right. So positive half cycle. I come this way, I go through him like he's not there, but there's a point, okay, positive half cycle, I've got a 0.7 drop across him, and I got a 10 volt drop across him, so that gives me 10.7 volts before I get clipped. So I'm going to come up, I get clipped, I come back down. Same thing happens on the other positive half cycle. All right, negative half cycle. Okay, on the negative half cycle, this guy becomes the 0.7. This guy becomes the 10. And I'm doing the same thing. I'm going down to 10.7 volts. And I come down, I get clipped off there, I come back up. Down, clipped off there, come back up. All right. And with that, I think that requires doing something on multisim, right? Assuming that I can find some 10-volt Zener, right? It would seem like that'd be the case, right? And because the circuit is so simple, we can do it on multisim. If it's something more difficult, then we wouldn't want to. All right, so we want a resistor.
Sure. Sounds like a good answer.
One, two, three of those guys. Now, if I use virtual Zeners, can I change them? I think I can. Can I?
No, I think
They're stuck at 5. Yeah, I can change that to 10.
yeah.
Yeah, what are you trying to tell me I can't do something? Yeah, so if I use the virtual ones,
I'll take a.
Grande 5. That's what you like.
okay, so I want 20 volts RMS. How much? I want 20 volts peak to peak. What's my RMS? So it'd be 20 times 0.707, right? So 14.14. I was supposed to have another resistor, wasn't I? I don't need no stinking resistor. Now, what would be better if I were to build these prior to coming to class, right? And it wouldn't take so long. All right, we'll just turn this on. Yep, exactly right. Oh, you want me to put something else on there?
It works perfect.
It looked perfect to me. I didn't see any problem with it. I don't understand. All right, so there's the red guy. There's this guy. And we'll ground him there. We'll ground him there. And we want one of them a different color, right? Blue, and we want these guys to be green, just because that'd be cool to have them green. Okay, there we go. Yep, perfect. All right, proof pot. Oh, you're gonna open this thing now. There. What did I say? And so what is it? 10.7? Is that what I said? 10.7?
Yep.
Minus 10.7?
Yep.
Fine. Well, I guess I can make it run now that I know that it works.
We had no doubt.
Yeah, you had no doubt, right? All right, good enough?
Good enough.
All right, well, we might need multisim again. All right, so now we have to go look for the study guide. And we know we have one, right? Where would it be? Yeah, it's probably going to have to be there. All you guys need is just a password to get on here, and then you can look at all these files. Industrial, whatever. Well, yeah, you need that too, but well, how come I don't have spring 1112 anyway? So, what are we doing? 17 to 18 study guide?
No, we want to see the 1718 test.
Oh, you want to say, okay, we'll open that one. Oh, darn. All right, so we got that one open. Then you want to look at the 1718 test as well?
Sure.
All right, so we'll open that one. Okay. So we'll do both the 1718 study guide and the 1718 test. And if we run out of time, then we'll just be out of time. All right, got that? All right, so which one do you want to do first? You want to do the test first?
Yeah. How many tests are there?
I make the test randomly off the exam bank, so it really doesn't matter. So, and I make it new every semester, so you know, there's going to be some percentage of the questions you see, those are the ones you miss. The ones you haven't seen yet, you'll probably get those right because you won't be confused. All right, so, what are we going to do? How come I'm missing my glorious thingy that comes out here that tells me I can copy something? Yeah, I don't know.
Just highlight it.
There it is, right there. Okay, I'm ready. So this is the right one? Yeah, this is the right one. Okay. So we probably don't need much room for space, right? So we'll just copy the first 7. Okay, excellent. With regard to, can you guys read that? Or do I, you can? We can't? I can make it a little bigger. Is that better?
Yep.
All right. With regard to reverse saturation current. Okay, so reverse saturation current is something that happens in a diode. Which statement is false? It's temperature dependent. All right, well, I guess that's probably true because when I changed it. And surface leakage current, blah, 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 are essentially the same thing. Is the amount of majority accounts for the majority portion of diode reverse current. That's true. Unless, of course, you burned it up. Is caused by thermal activity. That's probably true, too. So it looks like B. It's not the same as surface leakage current, because if it was, we wouldn't have it. That wouldn't make any sense. Okay, a Zener diode has a power dissipation rating of 750 milliwatts and a voltage rating of 5.6 volts. The maximum Zener current is, okay, so V is still equal to IR. Okay, so that's still true. And power is V times I, right? So I has to be the power, 750 milliwatts divided by 5.6 volts. All right, so where's my calculator? Oh, it's in my pocket. 0.75 divided by 5.6. Boom. 133.9. That looks like a B guy. All right. The forward bias silicone diode, forward bias silicone diodes in series with that, across that, the voltage across the resistor is. 9 minus 0.7, also known as 8.3. The forward, notice that this is really, all this is a math class, right, where you add, subtract, multiply, and divide. Yeah, so devices, it could be math 202, right? Be the same class, yeah. A forward bias silicon diode is in series with a 180 ohm resistor across a 15 volt source. What is the maximum power dissipation rating, the minimum acceptable power dissipation rating for the diode? Okay, so the voltage across the diode is 0.7, right? Alright, so we have 14.3 volts and we have 180 ohms. Okay, so 14.3 divided by 180, and we have 79.4 milliwatts. Okay. 0.4 milliwatts. So one would say that the correct answer is A, right? But the correct answer can't be A because the minimum acceptable has to be 20% more. Okay, so so that would 20. If I multiply this by 1.2, which I already have, I ended up with 95 milliwatts. And then I would say none of these are acceptable. The right answer is there. Because what I've done over the course of the years is I have removed the correct answer from the multiple choice things. Isn't that nice of me?
That's awesome.
I like that.
Yeah, awesome. Yeah. You like that? Yeah, that's just totally awesome. So, well, you have to, you know, if life was predictable, why would you want to be here, right? Yeah. Okay. A method by which some atoms complete their valence shell by sharing the valence electrons with other atoms is known as. Well, clearly it can't be that one because we never said that. And it can't be pentavalence because that would be 5, and nowhere is it talking about 5 of them sharing. So this is either recombination bonding or covalent bonding. Now, of those two phrases, which did my mouth say the first day of class? Did you say delta? That's correct. So delta would be correct. And if you remember your chemistry class from 10th grade, that would have been an easy one too. Okay, show of hands, how many skipped their chemistry class most of the time in 10th grade?
Never had one.
Yeah, exactly, yeah. All right.
When I was in 10th grade, they didn't have stuff like that.
Yeah, they didn't have things like, yeah, they didn't have chemistry way back then?
It just said, do not mix.
Yeah, my,
That was my chemistry.
yeah. 6. The diffusion of an electron across a Pn junction results in one net. Okay, so I diffused an electron. Okay, so here's my N material, here's my P material, and I've got one electron that went that way. That's how I read the problem. Positive charge in the P material, negative charge in the N material, negative charge in the N material, positive charge in the P material.
And
Positive charge in the P material, positive charge in the N material. So you're trying to tell me it's D? Is that what you're telling me? Yes, I agree. When I get rid of a negative charge from the N material that is doped negatively, it's going to be 1 electron, all of 1.6 times 10 to the minus 19th coulomb more positive charge there. All right. The ripple voltage of a full wave voltage doubler the ripple voltage of a full wave voltage doubler is 0, no, equal, no, is it twice or is it 4? Da 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 da. 4 times. Okay. Good enough? Let's see what okay, we're doing the test, so we're back to on the test. We made it all the way to there. This thing only goes to 12. I mean, talk about well, you know, you still would want to get half of them right. Get a halfway decent grade, I suppose.
I just think you can do 8.
I'm not going to do 8?
Not the way you was just doing it.
I suppose. Is this some comment on something?
Nope.
No, I didn't think so.
No.
Well, it doesn't look like I'm going to do any of them, so it doesn't really matter. So, all right, one more time. Think something happened? Okay, so we have 2 hours to do this test. So that means there's plenty of time to work on your lab after you've taken 15 minutes to do it, right? All right, so no excuses for being behind on your lab. A full wave bridge rectifier contains a full wave bridge rectifier. Okay, now that's right, it does, right? And this is also right. Okay, so there's 2 right answers here, right? Full wave rectifier, I could have 2 diodes, right? One like this, the other one like that. Or I could have 4 of them, and I could have a full wave rectifier. So now, oh, wait a minute, it says full wave bridge rectifier. Has to be B. A clipper is also referred to as a short, an open, a shunt, or a limiter. An LED and its current limiting resistor is being driven with a peak output of 9 volts. The LED has a range of 1.2 to blah, blah, blah. The forward current is 15 milliamps. Using a 20% guidance, what is the smallest standard value current limiting resistor? Okay, so I look at these guys. Are these all standard values? Well, heck, unless I'm looking at the chart, how am I going to know, right? I do remember 680 as being a standard value, 720, 250, and I think that 570 is too. So I think they're all standard values. 520? Yeah, that guy. I'm pretty sure they're all standard values, so we can't cross one off because it's, well, if you had one there that was 525, for example, then you could cross it out. But right now you can't. Okay, so back to where we're going. V is still equal to IR, I think. And we want to know, so R is going to be V divided by I. Okay, and so I got 9 volts, 9 minus 1.6 divided by 15. And then we're going to go 9 minus 2.2 divided by 15. And both of these are milliamps. Milliamps. So we're going to get the low one and the high one, see what they are. 9 minus 1.6 equals divided by 0.015. Boom. 375. Okay, 9 minus 2.2 divided by 0.015. Way to go. 9 minus 2.2 equals divided by 1.015. 453. Okay. Now, do we want to be do we want to multiply those guys by 0.8, or do we want to divide them by 0.8? And so we're going to divide by 0.8. Divide by 0.8, 566. So this becomes a 566, and 375 divided by 0.8 becomes a 468. So 566 appears to be my target number, so that makes the A guy the guy closest. And we probably want to have more room there to, huh? So what?
I'm trying to get the numbers you got, and I ain't getting them.
What are you not getting?
9 minus 1.6
9.
divided by 15 milliamps.
Yeah.
Equals
9
I got
minus.
493 microamps.
Yeah, I have 493.
Okay, you got 375 written down.
No, so you don't want that one.
Right.
So you want 493. Okay, so 493 divided by 0.8 gives me 616. 616. Now I'm going with B.
I'm not confused.
So how did I get
I have no idea
375?
how you got 375. And
Well,
to be
let's
honest,
see.
The second one, I didn't get the same answer as you neither.
Neither does he, because he just changed it.
And 466 for the second one. Yeah, 466. 9 minus 2.
1.6.
Oh, I just running, okay.
I know how I did it. This is how I did it. I took 9, I divided it by 1.6, and I divided my answer by 0.015. That's how I did it. So I fat fingered a key here. Instead of putting in a negative guy, I have a divide guy there. So what's your problem anyway? Why can't you do that on your calculator? So you could have figured out what I did. Just fat finger the wrong key. Now this new TI 6036 Pro, you in the light that I'm in, it's difficult to tell what those silver guys are, and so that's my excuse where the plus and the divide by guy is. So the minus guy and the divide guy look pretty much the same from where I sat. But now you know exactly what I did. I know that you wanted to know that. So it is possible to get my answer. Now it doesn't make my answer right, but it is possible to get it. Reflectors, rectifiers are diode circuits that convert DC to pulsating DC. DC, huh? Which one do you want? Charlie? All right, Charlie. So it converts AC to a pulsating DC. Yes, I agree. And then we have to put in a filter and a voltage regulator to get the pulsating part out. On a diode data sheet, the guaranteed operating characteristics are provided under. Okay, the guaranteed operating things. Mechanical characteristics? Oh, I hope not. Maximum ratings? The guaranteed ones? No. The minimum characteristics? No. B. Electrical characteristics. All right, so we're done with the test. Moving on to the study guide. And the study guide has the awesome 12 questions on it. I guess I was consistent, right? Always good to be consistent. So that means I should put
I think you're copying the same thing.
You think so?
Uh,
Oh yeah, I think so too. So that's the spring study guide.
oh, I see.
Is that the same as the spring test?
Yeah.
You know so?
Well, that's pretty good, wasn't it? I did good there, didn't I? I'm sure I won't do that again. But never can tell. I probably got carried away or something. So, let's see. I don't think I have the test gen for this class on this program, on this computer. We'll go looking for it. Because you probably want to know the answer to some question, like how many questions are there in the test bank, for example. And so, so I only have physics. I only have physics on my laptop, so that'd be an office machine. But I would imagine there's close to 100 questions per chapter to choose from. And they're all equally as simple as what you saw. All right, well, should we go home early? Oh, we can take attendance. I know. So if I know who you are, you can leave. If I don't know who you are, stay.